Okay, so this is a video on the t-distribution, which is an entirely new distribution for us, but it's a different type of bell-shaped and symmetric distribution. So it's kind of like the normal distribution, and we're going to use it where we would normally use a normal distribution, but it comes up because of certain circumstances. So, here's what happens. You have a, we were able to do, confidence intervals about a proportion because the proportions, the proportion estimate and the actual proportion, when we get central tendency, are the same. And the standard deviation of the proportion estimates, right, are square root of p times q over n. And this is like completely legitimate and easy to do. The problem is when we do samples about a mean, the sample mean is going to be close to the actual mean. But the standard deviation of the sample means is the standard deviation of the population over the square root of n. This is our problem, okay? Because the standard deviation here is something that we don't know. We don't get that from a sample, right? So we can get a p from a sample, we can get a q from a sample, we can get an n from a sample. So we get an n from a sample, we can't get a standard deviation. Like, we get the standard deviation of the sample, that's just S, which is going to be potentially quite different than the standard deviation of the population. So what we do is we ignore the normal distribution, and we use a distribution that's very similar that does not require us to actually know the population standard distribution. So this distribution is what we call a t-distribution, and it follows the formula x bar minus mu, so the sample mean minus the actual mean, over s times the square root of n. And you can solve this for the sample mean, for the population mean, without needing to know sigma. So nowhere in this formula is the population standard deviation. Now, that's all really upfront and technical stuff. Beyond this, most of the work you're going to do with this is in the calculator. And the work is like really kind of simple. It's very similar to what we did with confidence intervals of proportions, okay? So let's actually try to do this. All right, so let's say I want to know the average number of chocolate chips in a population of chocolate chip cookies. All right, so I'm going to take a sample of 32 of those cookies. I'm going to start counting chocolate chips. And I'm going to find that on average in that sample, there are 19.1 chocolate chips per cookie. Okay, and that the standard deviation for the sample is 2.1 chips. Okay, so now the question is like, where are the bounds for the mean of the population? Okay, so I'm going to use the sample to draw an inference about the mean of the population. And I'm going to do this, I'm going to try to create a 95% confidence interval for that distribution. Now, quite honestly, this is very simple. So let's show you how to do it with the calculator. Okay, so I need to find the t-interval. So I go stat, tests, and I go down not t-test, but t-interval, right? And I'm not taking this from a data set. I'm taking this from statistics. So I'm going to move that over to stat. And then I'm going to enter in the mean. So the mean in my sample was 19.1. My standard deviation was 2.1. And my sample size was 32. So I have a confidence interval level of 95%, and I calculate. And there it is. That's the answer. So I know that the mean of the, population has to be somewhere between 18.3 and 19.8 chips per cookie. And there we go. We've built a 95% confidence interval for the mean of the population, given a sample of that population that meets the criteria for central tendency, because we have more than 30 in the sample. All right, so there you go. That's a little bit on using the t-distribution.